Hello everyone, myself MUSKAN THAKUR. I am M.Sc student. Today we will discuss about the construction and working of MOSFET, and in this video we will focus on the enhancement type MOSFET, and in the next video we will focus on depletion type MOSFET. As we know that MOSFET is the abbreviation for metal oxide semiconductor field effect transistor. MOSFET is a most frequently used electronic device. In our previous videos, we have discussed about the BJTs and JFETs. MOSFET differs from JFET in the sense that in JFET, the conductivity of the channel between the source and the drain is controlled by the width of depletion layers on its either side. While in MOSFET, the conductivity of the channel is controlled by the voltage on an insulated metallic plate called the gate lying on the top of the channel. Thus, in MOSFET, the gate is insulated from the rest part by a layer of metal oxide, so it is also called the insulated gate field effect transistor. MOSFET is also an active device just like BJTs and JFETs. Now, what are active devices? Active devices are those devices which has the direct ability to control the flow of electrons or the current, while on the other hand, circuit components with no ability to control the flow of electrons are known as passive devices, like PN junction diodes, capacitors, and transformers, etc. There are two types of MOSFET, depletion type MOSFET and enhancement type MOSFET. Depletion type MOSFET is further classified as N-channel depletion type MOSFET and P-channel depletion type MOSFET. Same as enhancement type MOSFET is also classified as N-channel enhancement type MOSFET and P-channel enhancement type MOSFET. Construction-wise, there are many similarities in both the types of MOSFET, and it only has one difference. The difference is, in enhancement type MOSFET, there is no channel between the drain and the source. We have to enhance the channel in this type of MOSFET, while in the other hand, in the depletion type MOSFET, the channel between the drain and the source already exists. In this figure, the construction of N-channel enhancement type MOSFET is shown. First, we will see the larger area, that is in blue color. This is the substrate or body which is of the P-type semiconductor. The substrate is a layer over which we will fabricate our device. We can see that there are two small regions of N-type semiconductor. One of them is known as source and the other is the drain. We can see that there is no connection between these two regions, or we can say that initially the channel does not exist. To operate the device, firstly we have to enhance the channel between these two regions. That's why this device is called the enhancement type MOSFET. In this diagram, we can see that there are four terminals: source, drain, substrate and the gate. The gate terminal is not in direct contact with the substrate or the body. The gate is located over a very thin layer of silicon dioxide, and over this layer a metal contact is formed and the terminal is given the name gate G. The width of silicon dioxide is nearly equal to 1000 angstrom and also known as a gate oxide. The width of the silicon dioxide is kept very thin because we want the control over the surface by the gate electrode. There are four terminals: source, gate, drain and substrate or body. But in most of the circuits, the source and the substrate or body are connected internally. So we can say that there are only three terminals, that is source, gate and drain. Now we will understand the role of silicon dioxide layer. If we apply the positive potential to the gate with respect to the substrate or a body, the capacitor action starts. The gate and the substrate play the roles of two plates of parallel plate capacitor, while this SiO2 layer play the role of dielectric medium. Here in this figure, this is the gate terminal and this is the substrate terminal. And by the help of the external battery, we provide the positive potential to the gate and the negative potential to the substrate. And due to this, the positive charges starts to accumulate over the metal plate connected to the gate, and the negative charges starts to accumulate over the metal plate connected to the substrate. Here the role of the SiO2 layer is same as the dielectric medium between the two plates of the parallel plate capacitor. Since we know that the substrate is internally connected to the source, so this battery voltage is given by VGS, that is the potential difference between the gate and the source. Since we have discussed, the metal plate connected to the gate terminal has become positive and the metal plate connected to the substrate has become negative. So the electrons present here move towards upwards near the metal plate connected to the gate, and the holes are pushed down towards the substrate terminal. As we understood that the large number of electrons accumulate in this region, so this region becomes negative and a connection between the two n-type regions come into existence. On the other hand, we can say that a channel is developed or the enhanced between the source and the drain. In this figure, the channel is shown by the red color, and through this channel, the charges flow from source to drain. We can see that on increasing the VGS, the channel width also increases, but we notice that the width of the channel remains uniform throughout its length. It was all about the construction of N-channel enhancement type MOSFET. Now the device is ready to operate. Now we will talk about the working or operation of MOSFET. We have discussed that there are 4 terminals: source S, gate G, drain D, and substrate or body. And in most of the cases, the substrate or the body is connected internally with the source, and we also discussed that by increasing VGS, the width of the channel increases. When VGS is greater than a particular voltage, the channel width is sufficient to allow the significant flow of current IT. This particular voltage is called threshold voltage, denoted by VT. It is an important parameter in MOSFET. The voltage that results in the significant amount of current to flow from source to drain is known as threshold voltage. Current will flow between drain and source only when the source and drain will be at different potentials. So, we connect the positive terminal of the battery to the drain and negative terminal of the battery to the source. Now we apply positive voltage to the gate G with compared to the source S by introducing another battery. Now we want to find out the effect of VDS on the depletion layer, and because of this purpose we need to find out the voltage VGD. On applying the Kirchhoff's law in this loop, we can write the equation for voltage. The voltage of drain VD can be written as Vg minus Vgs plus Vds. This equation can also be written as Vg minus Vd equal to Vgs minus Vds. The voltage difference between the gate and the drain can be given as VGD, so this equation can also be written as VGD equal to Vgs minus Vds. We have connected 2 batteries. One of them is between source and gate. Its voltage difference is denoted by VGS, and the other battery is connected between drain and source. Its voltage difference is denoted by VDS. Now we will understand the working of MOSFET by varying drain source voltage VDS. In the case 1, when drain source voltage VDS is equal to 0 volt, when VDS equals to 0 volt, then VGD will become equal to VGS. This indicates that source and drain are in same potential, then the width of depletion layer will be uniform along its length. In this case, the width of channel depends only on the value of gate source voltage VGS. By increasing VGS, the width of channel also increases but remains same throughout its length. Now, the second case, when VDS is greater than 0 volts, means on increasing VDS, the drain becomes more positive and the source become more negative. Since the drain is more positive or reverse biased, so the depletion region near the drain becomes wider Because of this region, the channel near the drain becomes narrow. And the source is more negative, or we can say it is more forward biased, so the depletion region near the source becomes narrow, and because of this region the channel near the source become wider. So in this figure we can easily observe that the channel shown by the red color is narrower near the drain and it is wider near the source. So as we increase VDS, we observe that the channel gets narrower near the drain with respect to the source. Now the third case. When we continuously increase the VDS, then a situation arises when the channel near the drain becomes extremely narrow. On continuously increasing VDS such that VDS equals to VGS minus VT, on putting this value in our Kirchhoff's equation, we find that VGD becomes equal to VT. This condition is known as pinched off condition. In this situation, the width of channel near the drain becomes 0, but practically it is not possible. The voltage VDS corresponding to this situation is known as pinched off voltage and it is denoted by VD saturated. In this video, we have discussed about the MOSFET, types of MOSFET and the construction and working of enhancement type MOSFET. We will discuss the current voltage characteristic curve of enhancement type MOSFET in our next video. So please watch the upcoming video of our channel. Thanks for watching.